Group 4's emerging technology is air purification through microalgae bioreactors. Group 4 consists of Angelo, Henry, Tarandu, Shaylin, Caitlin, and TJ. Microalgae bioreactor technology has been studied for multiple useful purposes, such as energy production and wastewater treatment, but it has shown the ability to also serve as a nature-based solution for air purification. Research is still in its infancy, but the influence to share this technology came from the following articles. References highlighting our technological focus is cited from an article published in the National Public Library of Medicine, endorsing nature-based solutions with emphasis on microalgae as a promising technology for treating indoor air quality. The first photobioreactor built for urban settings in Serbia, referred to as Liquid 3, that received an Innovation Award in Sustainability. This research was initiative from the Institute for Multidisciplinary Research from the University of Belgrade and supported by United Nations Development Program in Serbia. A similar approach to removing air pollutants was also highlighted in Nepal. This is the International Center for Integrated Mountain Development and a regional intergovernmental learning and knowledge sharing center serving 8 regional members countries of the Hindu Kush Himalayas.
At its core, microalgae bioreactors can be broken into 4 basic steps. The first step is air extraction, where air containing a high level of CO2 or other pollutants is directed towards and captured by a bioreactor. Once in the bioreactor, the microalgae is exposed to natural or artificial light, causing photosynthesis to take place. The CO2 from the intake air is used up in this process and then fixed to a microalgae biomass. As a result of the photosynthesis in step 2, clean air is released from the reactor, increasing the O2 levels and reducing the CO2 levels in a surrounding area. The last step is biomass collection. The biomass produced in step 2 is collected from the reactor and can be reused in a variety of fashions, such as bioenergy feedstock or fertilizer. The primary function of this technology is CO2 reduction and oxygen renewal in the surrounding area, but there are some other key details to note. A big interest in this technology is its potential for integration into architectural and mechanical systems. For example, microalgae bioreactors offer both aesthetic benefits, such as visual greenery and art installations, as well as functional benefits, such as shade devices and thermal regulation of buildings. This system can also be modular in nature, making them adaptable and scalable for specific locations. It's also worth noting that while artificial light can be used for this process, it can operate solely off of solar power energy input. Therefore, this system can minimize the electricity needs of air filtration compared to other mechanical systems.
Let's look at the numbers to understand why innovative air pollution technology is so critical. As you can see, urban areas generate a staggering 75% of the world's carbon dioxide emissions. And a huge piece of that puzzle is our buildings, which are massive consumers of energy. This problem directly affects our health because we spend the vast majority of our lives, over 90%, inside these buildings. This is where the risk becomes personal. The World Health Organization and other studies connect poor indoor air quality to more than 5 million premature deaths every year. This highlights the urgent need for effective, localized solutions like the ones we are discussing today. Now, let's look at the numbers that demonstrate how algae bioreactors directly address these crises. In Kathmandu, Nepal, the installation of just 2 algae bioreactors has already produced more than 12,000 liters of oxygen. And impressively, this was achieved by a machine with a footprint of less than 35 square feet. But how does this efficiency compare to nature's own air purifiers? Our case study from Serbia provides a clear answer. The researchers behind the Liquid 3 photobioreactor found that microalgae inside are 10 to 50 times more efficient at binding carbon dioxide than trees. A single one of these units can do the work of two 10-year-old trees or 200 square meters of lawn. Finally, let's look at the potential for scaling this technology in our built environment. The BIQ house in Hamburg, Germany, is a real-world example. Its facade, covered in 200 square meters of algae photobioreactors, can remove up to 6 tons of carbon dioxide per year.
Looking at some specific examples, algae bioreactors can utilize carbon dioxide and other air pollutants, wastewater, and algae produce biomass and oxygen. It traps air, water, and solid waste within the system, which helps mitigate climate change. Specifically, it can trap carbon dioxide, nitrogen oxides, sulfur dioxide, water vapor, and particulate matter from industries, factories, boilers, hospitals, waste incinerators, and chimneys. The nutrients for the algae come from the wastewater, and this method is highly useful and provides a sustainable method for wastewater and has the potential to contribute to a circular economy due to its self-sustainability. Liquid 3, an algae air purifier. It is used because there's often a lack of free space for landscaping in urban areas and cities. The goal of this is to implement it into urban pockets where there's no space for planting trees. Liquid 3 can help reduce greenhouse gases, gas emissions, and improve air quality. It is a 600-liter aquarium with algae that binds carbon dioxide and produces pure oxygen through photosynthesis. It is designed to be a bench, charges phones, and has solar panels, and it is 10 to 50 times more efficient than trees, since trees cannot survive in heavy pollution, but algae can. It uses a single-celled freshwater algae that exists in ponds and lakes, and it is resistant to high and low temperatures and does not require any special maintenance. And then specifically, it removes biomass created by dividing algae, which is then used as fertilizer. New water and minerals are added about every month and a half, and the algae can then grow indefinitely. This system is used in various ways, such as water treatment, compost for green areas, production of biomass and biofuels, and air purification from exhaust gases and particulate matter.
So we have compared microalgae bioreactors to artificial trees and biofiltration systems. And microalgae bioreactors take away using sunlight to absorb the CO2 and releasing oxygen and biomass such as fertilizer or biofuel, ideally in dense urban areas where you have a small area to build one, whereas artificial trees and biofiltration systems are compact but artificial, and then biofiltration systems are more for like the industry and take out away VOCs and odors, but require a much larger space. Algae can thrive in high polluted air temperature, low oxygen environments, while trees can't, and it can convert urban waste into valuable outputs like biomass. And then the cons are it requires sunlight and nutrients to sustain large growth, and needs regular maintenance to harvest the biomass and to clean the system. And performance can vary with temperature and light availability depending on location.
To conclude, algae bioreactors aren't here to replace trees or natural ecosystems. They're here to fill the gaps in dense urban areas where planting greenery just isn't possible. What makes them truly exciting is the innovation behind them. We're taking microalgae, one of Earth's oldest life form, and using it in a high-tech way to address modern environmental challenges. It's a powerful mix of science and nature working together. Public installations like Liquid 3 help make this technology more familiar and accessible, but for real impact, governments and city planners need to get involved, investing in these solutions, creating supportive policies, and making them part of a broader sustainability strategies. While early projects show a lot of promise, there is still work to do. More research is needed to tackle challenges like maintenance, energy use, and seasonal challenges. With the right support, these systems can become smarter, more efficient, and more widely adopted. In the end, an algae bioreactor isn't just a piece of equipment, it's a message, a symbol that even in the heart of a city, we can breathe differently. This concludes our presentation. Please add any questions to the discussion board. Thank you.